In this video, we're going to do some examples using integration by parts to evaluate integrals, both definite integrals and indefinite integrals. So we're going to start with a definite integral. Now, if somebody gives you a definite integral and you want to use integration by parts, the first thing is usually just to ignore those limits of integration, at least temporarily. Because the idea here is that this is going to be equal to, using the evaluation theorem, f at pi minus f at 0, where this f is an antiderivative. So capital F prime of x is equal to x squared sine of x. So usually what you'll do is you'll ignore the limits of integration and just do the integral, the indefinite integral, x squared sine x dx. Because this will give you an antiderivative. Well, it'll give you the general antiderivative, and then you just ignore the plus c, or let plus c be equal to 0, and that will give you the antiderivative that you need for this computation right there. So that's what we'll do. So we're going to ignore the 0 to pi for right now, but just for right now, we're going to have to go back to that. So how do you do this? Well, this is a polynomial, x squared, times a trigonometric function. So in a case like this, you usually want to let u be equal to x squared, the polynomial, and dv be the trigonometric function. The reason for that is that if you differentiate the polynomial, you get something simpler. 2x is a degree 1 polynomial, which is less complex than a degree 2. And v is an antiderivative for sine, which is the opposite of cosine. Cosine is at least no more complicated than sine, so you haven't really lost anything there. And you've gained over here. Maybe it doesn't seem like a lot, but you've reduced the polynomial from degree 2 to degree 1. So this is going to be equal to uv minus the integral of v du. So this is u, x squared, times v, so there's a minus cosine x, minus the integral of v, minus and minus is plus, cosine of x times 2x dx. Well, now we've got another polynomial times a trig function, so we're going to have to do this a second time. But always remember that if your first u was a polynomial, then your second u should also be the polynomial. So you're going to have u is equal to 2x, and then dv is everything else. So that's cosine x dx, like that. So if u is 2x, then du is 2 dx. And v is an antiderivative for cosine, which is sine of x. So now we plug all that back into our integral. So we're going to have minus x squared cosine of x plus, and now it's going to be uv minus the integral of v du. So you just plug in everything. So it's minus x squared cosine of x plus u is 2x times v is sine of x minus the integral of v, sine x, times 2 dx. Okay. So you can take that 2 out if you want. So you're going to end up with minus x squared cosine of x plus 2x sine of x. And then you've got minus 2, and an antiderivative for sine is negative cosine of x plus c. Well, minus and minus is plus, so you don't really need those minus signs there. Now this whole expression here, that's your capital F at x. So your definite integral from 0 to pi of x squared sine x dx is going to be this expression, minus x squared cosine x plus 2x sine x plus 2 cosine x. All of that evaluated between 0 and pi. So the first one, first we have the upper limit. So it's going to be minus pi squared times cosine of pi is a negative 1, plus 2 times pi times sine of pi is 0, plus 2 times cosine of pi, again, is a negative 1, minus, and now you have 0, you plug zeros in everywhere. Well, this is going to be, this one is going to give you 0, because it's 0 squared times cosine of 0, plus 2 times 0 sine of 0, so that's another 0, plus 2 times, well, cosine of 0 is 1. So you got to be careful about that. Don't just throw zeros in everywhere. So what do you end up with? Well, that term goes away, that term goes away, that term goes away, and you end up with minus a minus is plus. So it's pi squared minus 2, and then minus 2. So you end up with pi squared minus 4. And that's your answer. So that's the first one. That's the first example. Let's do another example. Here it is. Example B is the antiderivative, the indefinite integral, or the general antiderivative of arcsine. Now arcsine is an inverse function. So when you see an inverse function and you want to use integration by parts, usually that's going to be your u. Now this one is one of those slightly misleading ones, because at first it doesn't look like you should use integration by parts. Integration by parts is something you do when there's a product. There doesn't really seem to be a product here, but it's misleading. Arcsine of x dx is arcsine of x times 1 dx. So u is our arcsine, and then dv is 1 dx. dv equals 1 dx, or you can just write dx. So if u is arcsine, we need the derivative. But we know the derivative. It's 1 over the square root of 1 minus x squared. That's the derivative, dx. And v is the antiderivative of 1, which is just x. So that is our antiderivative v. Okay, so now we just use our formula. So this is going to be uv minus the integral of v du. So we plug in all of the pieces. U is arcsine of x times x minus the integral of v, which is x, times du, which is 1 over the square root of 1 minus x squared dx. Okay, so this is x times arcsine x minus, and this is an integral, let me just rewrite it like this, 1 over the square root of 1 minus x squared times x dx. Now I left a little bit of space there because we're actually going to use a substitution. You can do this using the method of substitution. The inside function is 1 minus x squared. It's inside the radical. So what I'm going to do is I'm going to well, I don't want to use u because I've already used u, so it's common to just use w as 1 minus x squared. So that this thing right here is going to be 1 over the square root of w. If w is 1 minus x squared, then dw is minus 2x dx. So I have an x, but I need to put a minus 2 in front of it. Let's just change the color. Minus 2. But if I put a minus 2 out there, I have to put a 1 over minus 2 here. Now this is my dw. So let's rewrite this. So we're going to have x arcsine x minus a minus 1/2 is plus 1/2 the integral of w to the negative 1/2 dw. 1 over the square root of w is 1 over w to the 1/2. That's this thing right here. 1 over the square root of w is 1 over w to the 1/2, which is w to the minus 1/2, which is why I have that there. Okay, so this is a power function, so we use the power rule. So it's x arcsine x plus 1/2, and now we add 1 to the exponent and divide by that new exponent. And then you throw on a plus c. Well, this 1/2 is going to cancel with that 1/2, and you're just going to end up with x arcsine x plus the square root of w plus c. But don't leave it as w. You have to plug in this 1 minus x squared. So you end up with x arcsine x plus the square root of w, which is 1 minus x squared, plus a constant of integration. And that's your answer. Let me just fix the 1, and there we go. That's our second example. And at any time, you can always check these just by computing the derivative. So let's just do that. Check the derivative with respect to x of x arc sine x plus, and this is 1 minus x squared to the 1/2, and the derivative of c is 0, of course. Well, for the first one, you have to use not integration by parts, you have to use the product rule. It's x times arc sine x, so you have to use the product rule. We shouldn't be surprised by that because we used integration by parts. Usually if you use integration by parts, the check means product rule. So it's the derivative of the first, which is 1 times arc sine, plus the first times the derivative of the second, which is 1 over the square root of 1 minus x squared. And now we want to do this one. That's the derivative of the first term. So this derivative goes to that. And now we want to compute the derivative of 1 minus x squared quantity to the 1/2. And for this we have to use the chain rule, which again shouldn't be a surprise because we used a substitution somewhere along the way. Substitution undoes the chain rule. So this is going to be 1/2 times 1 minus x squared to the minus 1/2. Then you have to multiply by the derivative of negative x squared, which is minus 2x. Okay. Now that negative 2 cancels with that negative 2. This term is the same as that term, but there's a minus sign, so they cancel. And what are you left with? You're left with just arc sine of x. And so it turns out that we did this problem right. So let's do another example. This is where the problems start getting a little bit sneaky. Here we have sine of the square root of x. Now this one may not look like an integration by parts problem, and on the face of it, it isn't, but you can do this problem using integration by parts. But before you do that, you have to make it look like it has multiple parts. And in this case, the way to do that is to use a substitution. So if you look at this problem right there, it has a composition. And inside that composition, or it's inside the sine function, you have a square root. So that's going to be your inside function. So we're going to start by making a substitution. We're going to use integration by parts later, so I'm going to use a u and a v for that. So I'm going to start off by letting w be the square root of x. So if w is the square root of x, then this term right here is sine of w. Now that's great and all, but what about that dx? You have to convert that into w's as well. There needs to be a dw here. Now, how am I going to make that happen? Well, I can differentiate this. I can differentiate w because w is x to the 1/2. So dw is going to be 1/2 x to the minus 1/2 dx. Or another way of writing that is dw equals 1 over 2 square roots of x dx. Now, you're not going to find that over here. There's no 1 over 2 square roots of x there. So you might think that we're in trouble, but this square root of x should look familiar because that was our original w. This thing right there is w. So that means dw is equal to 1 over 2w dx. Now this 2w, it wants to be over here with the other w. So this is 2w dw equals dx. And that is exactly what we need to substitute in. So this thing right here, dx is 2w dw. So what do we end up with? We have the integral sine of w times 2w dw. Now this looks like problems that we've seen before. The integral of 2w sine w dw. There we go. Now we can actually take the 2 out. So this is 2 times the integral of w sine w dw. And now we can use integration by parts on this one. You let u be equal to w, and then dv is everything else. So u equals w, dv equals sine of w dw. Let me just move it down a little bit so we have a little bit more space there between those two computations. So if u is w, then du is the derivative, dw. And v is the antiderivative, or an antiderivative of sine, which is something we've seen before during these problems, cosine of w, minus cosine of w. So now we use, so this is going to be 2 times u times v minus the integral of v du. Just plug everything in. 2 times u, w, times v is a negative cosine of w minus the integral of v, so it's minus cosine of w du, which is dw. Now here you've got a minus, which is a plus. So you've got minus, well, let's not forget the 2, minus w cosine w plus the integral of cosine w dw. Now this one is has an elementary antiderivative, so we can compute that in a fairly straightforward way. Minus w cosine w. Okay, an antiderivative of cosine is sine. Now we're looking for the general antiderivative. The indefinite integral is the general antiderivative, so we put a plus c there. Now we're not done with this problem because our problem started off in terms of x's. We had x's here, so it needs to finish in terms of x's. So wherever you see a w, you need to put in a square root of x. W equals the square root of x. That's easy enough. So we're going to have, well, let's multiply that 2 in there as well. So we're going to have minus 2 times w cosine w, that's supposed to be a w, plus 2 sine w plus a constant. And now let's plug in that w equals the square root of x. So minus 2 square root of x cosine square root of x plus 2 sine square root of x plus c. And there's your answer. Let's do another example. Here it is. D is equal to x arctangent of x. So here again, we have a polynomial, a degree 1 polynomial, times an inverse function. So you might be tempted to let u be equal to x and dv be equal to everything else. The problem is if dv is arctangent, then you need v to be an antiderivative. And maybe we don't know an antiderivative for arctangent. Usually, if you have an inverse function, you want that to be your u. So that's going to be your u. You let u be equal to arctangent of x, and then dv is everything else, x dx. Let's just rewrite it. So it's arctangent x times x dx. So this is u dv. And of course, this is going to be u times v minus the integral of v du. The reason we choose u to be arctangent is that we know how to differentiate it. Du is the derivative of arctangent is 1 over 1 plus x squared dx. We don't know an antiderivative for arctangent, or maybe we don't, maybe we do, maybe we don't. Right now, we haven't talked about it in any of these videos, so we don't know the antiderivative of arctangent. But we certainly know the derivative. The derivative of arctangent is 1 over 1 plus x squared. All right, and v, well, v is an antiderivative for x, so that's going to be x squared over 2. So we've gained a little in complexity there. We went from degree 1 to degree 2. So things got a little bit more complicated over there, but things got a lot simpler on the other side. We started out with something which was a complicated inverse trig function, and we ended up with 1 over a polynomial, which is something we can probably handle. And in fact, it'll work out just fine in this case. So let's fill in the blanks. U is arctangent, times v is x squared over 2. Then it's minus the integral of v, which is x squared over 2, times du, which is 1 over 1 plus x squared dx. Now the first term here, that might look complicated, but that's fine. You don't have to do anything with it. You're done with that term. So this is equal to x squared over 2 times arctangent of x. And we're going to subtract, well, let's take out the 1/2 just for fun. And then we have the integral of x squared over 1 plus x squared dx. All right, now we might have a problem. In particular, what do we do about that? That's certainly not something we've seen before. So we have this new type of thing that we want to integrate, and we've never seen it before. So we don't know it just off the top of our heads. We don't have it in our list somewhere. So what are you going to do? Well, the way to approach a problem when you've never seen it before is try to make it look like something that you have seen before. And here's the trick, if you can call it that. X squared over 1 plus x squared is equal to x squared plus 1 minus 1 over 1 plus x squared. That's supposed to be a 2. Now what have I done here? Well, I haven't done a whole lot. I've just added and subtracted 1. So I can do that because 1 minus 1 is 0. Otherwise, everything's the same. So how does that help? Well, this is x squared plus 1 over 1 plus x squared minus 1 over 1 plus x squared. Magic. It's magic because x squared plus 1 over 1 plus x squared, that is equal to 1. How does that help? Well, what have we got? We've got x squared over 2 arctangent of x minus 1/2 times the integral of, let's replace x squared over 1 plus x squared with this new expression here. So it's 1 minus 1 over 1 plus x squared dx. Now at first glance this might seem like we haven't gained any ground, but we actually know an antiderivative for both of these terms here. Well, certainly the antiderivative for 1, or an antiderivative for 1, is x. So this is going to be equal to x squared over 2 arctangent x minus 1/2, and now we're integrating term by term. The antiderivative of 1, or an antiderivative of 1, is just x, minus an antiderivative of 1 over 1 plus x squared. Now that should look a little bit familiar because we've just seen it right here. We saw that the derivative of arctangent of x is 1 over 1 plus x squared. Now we want the antiderivative of 1 over 1 plus x squared. So that's just going in the reverse direction. So we're just going to go in that direction now. So it's just arctangent of x. And then we throw in a plus c because we're computing an indefinite integral. So this is going to be x squared over 2 arctangent x minus x over 2 plus 1/2 arctangent x plus a constant. And there you have it.